Hello students, welcome to the course on Analog and Digital Communication System. Myself, Dr. Surajit Boshak, Assistant Professor, EC Department of Guru Nanak Institute of Technology, Kolkata. Today, we are starting lecture number 3 from the third module, that is Pulse module. In the last class, we have discussed on delta modulation. Delta modulation actually transmit 1 bit per sample. Here, the present sample value is compared with the previous sample value. If the present sample value is higher than the previous sample value, then binary 1 is transmitted, and if the present sample value is lower than the previous sample value, then binary 0 is transmitted. So in the figure, see, the first sample value is naturally higher than the previous sample value. So, sorry, for the first sample is this sample value is naturally lower than the previous sample value. So binary 0 is transmitted. Now the second sample is higher than the previous sample. So binary 1 is transmitted. Again, these are the higher, then 1 is transmitted. And now here, see, this sample value is lower than the previous sample value, then correspondingly 0 is transmitted. So that part already we covered in the last class, and correspondingly we also discuss about the transmitter and receiver circuit. Now the question is, obviously the advantage is it has the bandwidth reduction. The bandwidth of the delta modulator is only FM because it only transmits 1 bit per sample. Now the question is there any disadvantages for delta modulation? Yes, two disadvantages are present. One is called slope overload distortion and other is called granular noise or ideal noise distortion. Now, what is slope overload distortion? When the rate of rise of input signal is so high that the staircase signal, that is the quantized signal, staircase means quantized signal, cannot approximate it. The step size becomes too small. It needs to be large. The step size needs to be large. Then the error between the original signal and the staircase signal is called slope overload distortion, as it is shown in this figure. And what is granular noise? When the step size becomes too small, just reverse of the slope overload. When the step size becomes too small as compared to the small variation of the input signal, then the error between the original signal and the staircase approximated signal is called granular noise. Then the question is, how these two disadvantages can be solved? So to overcome these two errors, what should we do? Step size should be variable. Step size will be large when the slope of the input signal is high, and step size will be small when the slope of the input signal is low. So step size needs to be variable and it depends upon the slope of the input signal. That is why another modulation technique comes, which is called adaptive delta modulation. And before we move to the adaptive delta modulation, I'm giving you a problem. For a sinusoidal signal, A cos omega mt, find the condition for no slope overload if step size is delta and sampling period is Ts. It is based on the slope overload distortion. So the sine wave is xt equal to A cos omega mt. It may be noted that the slope of xt will be maximum when derivative of xt with respect to t will be maximum. So the maximum slope of delta modulator is step maximum slope equal to step size by sampling period, which is delta by Ts. So we know that slope overload distortion will not take place if slope of sine wave is less than slope of delta modulator. That means maximum of d dt xt, that is the maximum slope of the sine wave, will be less than slope of the delta modulator, that is delta by Ts. So maximum of d dt xt is A cos omega mt less than delta by Ts. So differentiating A cos omega mt and takes the maximum, it will be A omega m less than equal to delta by Ts. So A always less than or is equal to delta by omega m into Ts. That is the condition for no slope overload. And the reverse, that is A greater than delta by omega m Ts, which is the condition for slope overload. So this question may become, here it is written that the condition for no slope overload condition, the questions may become the condition for slope overload. So in the case of the condition for slope overload, A always greater than delta by omega m into Ts. Okay. Now move for the adaptive delta modulation. So adaptive delta modulation is a modulation technique in which we can solve the disadvantages of delta modulation, that is slope overload distortion and granular noise distortion can be removed by adaptive delta modulation. In adaptive delta modulation, the step size is not fixed. It is step size varies according to the slope of the input signal. See here, the step size here is delta 1. Now in this portion, the slope is higher compared to the lower part, so the step size becomes larger. So the step size is here delta 2, which is larger than delta 1. So again here the slope is higher. So in this part the step size is say delta 3 is higher than delta 2. So step size is variable according to the slope of the input signal. This process is called adaptive delta modulation. Now, what is the circuit for transmitter? Remember that this part is actually the same circuit for delta modulation. Just one thing is added here, that is the logic for step size control. So from here output, or better to say BNTS, from here the signal goes to logic for step size control, and all others are same. And similarly, for the case of receiver, this part, that is the delay part, or better to say it is an accumulator with followed by low pass filter, is this part is same as delta modulation. Only the exceptional part for ADM is logic for step size control. This part is exceptional for the case of receiver. Next is another modulation or source encoder technique is present for bandwidth reduction, which is differential pulse code modulation, or it is abbreviated as DPCM. First, say in DPCM, this is the analog signal, dotted signal is the analog signal. And after that, following the principle of quantization, suppose these are the quantized value. Say the value is say 0, 1, 0. In here, the code is 4, that is 100. In this point, the code is say 101. Similarly, here, code is 6, that is 110. Same as. One 110 is valid for 4, 5, and 6 TS. Now for 7 TS, it is 101, that is 5. For 8 and 9 TS, it is 101, that is 5. So it may be observed that the sample of a signal are highly correlated with each other. The difference between the present sample value and the previous sample value does not differ so fast. The adjacent two samples carries the same information with a little difference. When these samples are encoded by a standard PCM system, the resulting encoded signal carries some redundant information. Here, in 2TS and 3TS, the first two bits are same, that is 100, and for the case of 100 and 101. See, the first two bits are same. The difference present in only the last bit. So the first two bits are redundant. So similarly, for 4TS, 5TS, and 6TS, same information transmitted 3 times. That is 110, same information. So these 3 bits are redundancy. Now, if redundancy is reduced, the overall bit rate will also be reduced. This type of digital modulation scheme is known as differential pulse code modulation. In this case, just redundancy bit are reduced. Therefore, the overall bandwidth will be reduced. So DPCM is a technique by which we can reduce or we can suppress the redundancy bits. Okay. Next is the multiplexing using PCM signal. One of the advantages of PCM signal is the multiplexing. We have already noted the advantage of converting an analog signal into a PCM signal when the signal must be transmitted over a noisy channel. When a large number of PCM signals must be transmitted over a common channel, multiplexing means many to one. Many signals transmit into one common channel. So when a large number of PCM signals must be transmitted over a common channel, multiplexing of these PCM signals are required. In this case, we discuss about the multiplexing methods for PCM waveform. The basic time division multiplexing scheme is called the T1 digital system, which is used to convey multiple signals over telephone lines using wideband coaxial cable. It accommodates, remember that it accommodates 24 analog signals, which can refer here from S1 through S24. And each signal is band limited to 3.3 kilohertz and it is sampled at the rate of 8 kilohertz. So band limiting can be done by using the low pass filter. And after that, it is sampled at 8 kilohertz by the sampling switch or commutator. Here, a commutator or rotating switch is present, which is sampled one by one, or it is like a chopper. And the sampling rate is 8 kilohertz. And the Nyquist rate if the cutoff frequency of low pass filter is 3.3 kilohertz, then the Nyquist rate is 6.6 kilohertz. Next, each of the time division multiplexed signal, still analog signal there, is next analog to digital converted using PCM transmitter or compander. Now the resulting digital waveform is then transmitted over a coaxial cable periodically at approximately over 6,000 feet interval approximately. The signal is regenerated by the amplifiers called repeater or regenerative repeater. The repeater eliminates the noise and other distortion. All the destination, the signal is at the destination, the signal is again compended, decoded or demultiplexed at the PCM receiver and making available individually. Here again a commutator switch SW2 is present and which give the signal individually to the destination, say S1, S2 or S24. Now the condition is here two commutator is present or rotating switch, say SW1 and SW2. The first condition is these two rotating switch must be synchronized and it rotates at the same revolutionary speed. Synchronized means, suppose here SW1 start from S1, then S2, then S2, after goes to then S24, like that. So SW2, the switch SW2, it must start from work S1 also. If SW1 start from S2, then SW2, this switch also start from S2. So these two switches SW1 and SW2 needs to be synchronized. And second condition is the revolutionary speed, that is the 8 kilohertz or 8,000 per second. These two should be same for SW1 and SW2. So the commutator sweeps continuously from say S1 to S24 and then again S1 at the rate of 8,000 revolutions per second, thereby providing 8,000 samples per second of each signal. And I already mentioned that each sample is encoded into 8 bits, thus providing 2 to the power 8, that means 256 quantization labels of each signal. So what is number of bits? First we have to calculate number of bits per frame. First you should know what is frame, bits per frame. So first you should know what is frame. Suppose that it starts from commutator starts sampling from S1, then goes to S2, S3, S4, and at the end it goes to S24. This called one frame. Then again start the next frame, that is which is starting from S1. So S1 to S24 is called one frame, and each frame is encoded, each sample is encoded into 8 bit. So total number of bit per frame is 24 into 8, that is 192. Say 8 bits, 1, 2, 3, 4, 5 samples. That is the S1, S2, S3 voice channel. Up to 24 voice channel are present. And each, that is called one frame. This part is called one frame. And each sample is encoded into 8 bits. All are the 8 bits. So, how many total bits, number of bits present in a frame? 24 into 8, that is 192 bits present in a frame. Clear? Okay. Next is the frame synchronization. What is frame synchronization? See, the commutator speed 8,000 samples per second. That means 8,000 revolution per second. In 1 second, think it. In 1 second, the commutator revolution 8,000 times. Very high speed. So, in that case, no one can separate one frame to another frame, where a frame start, where a frame end. So to separate information bits correctly at the receiver, it is necessary to be sure where each frame begins or where each frame ends. So how it can be done? So a frame synchronizing bit is necessary. That means a frame synchronization bit identifies from where a frame start. So to provide such synchronization, an extra single bit is added immediately after preceding the 192 bits. So when a frame starts, at the starting of each frame, and another extra bit is added, which is called the frame synchronizing bit, which actually does not carry any information. It signifies from where a frame start. So now the 192 bit slots assigned to the encoded signal together with an one extra bit. So now total number of bits per frame is 192 plus 1, that is 193. Now the question is frame synchronization bit. I'm telling you frame synchronizing bit. So bit means either it is 0 or 1. So again same question. In these slots, that is the samples, the information carries in binary form, either 0 or 1. So one can, how it is it differ from the frame synchronization bit? Those are both in binary form. So one can easily say that frame synchronizing bit also a information bit. So how it is identifies that it is a frame synchronizing bit? The receiver, there may be a chance that the receiver takes it as an information bit. So to solve the problem, 12 successive F slots or frame synchronizing slots are used to transmit a 12-bit code. Say any code, say it is, say here a 12-bit code is present. Say the code is 110 0, sorry, 110 111 00 1 000. Now this code is transmitted repeatedly once every 12 frames and is used at the receiver to establish synchronization. That means in the first frame, say the first one is transmitted. In the second frame, then second one is transmitted for the frame synchronization bit. In the third frame, so this 0 is transmitted for the frame synchronization bit. Similarly, for 12th number of frame, this 0 is transmitted for the frame synchronizing bit. Now, then again 13 number of frame, the first one is transmitted. 14th number of frame, this one is transmitted for the frame synchronization bit. So this is repeated, this code is repeated every 12 frame. So no one can say that the information always repeated in every 12 frame. It may be repeated 1, 13, but after in 8,000 revolution per second, in every 12 frame, it should not repetitive. The repetitive comes only for the frame synchronization bit. So in that way, we can identify the frame synchronization bit, or better to say, where a frame start. Next is the bit rate. Bit rate calculation. Each signal is sampled 8,000 times per second. So that a complete frame occupies 1 by 8,000 second, that is 125 microsecond is required to transmit a complete frame, and in a complete frame, total 193 number of bits are present. So bit rate is 193 by 125 Mbps. So that is 1.544 Mbps, megabit per second. Okay. So for T1 digital system, it is very much important. So for T1 digital system, the bit rate is 1.544 Mbps. Then is the signaling. A telephone system must be able to transmit not only the speech communication but also certain other signaling information. This information need to be conveyed that a call is being initiated, that a call is being terminated, specifying address of the called party when analog transmission is employed. The signaling information is often conveyed over a channel separate from that which carries the voice. But in the case of T1 digital system, a process is called bit slot sharing. Again, I am repeating, in T1 digital system, a process is called bit slot sharing is used to allow the single channel to transmit both voice and signaling. How? During 5 successive sampling, that means hence during 5 successive frame, each sample is encoded into 8 bits. But during the 6th frame, the samples are encoded into 7 bits. And the 8 bit, that is the LSB part, being used for signaling. So this pattern is repeated every 6th frame. See, this is channel 1 for channel 2 and channel 24. So it is called one frame. These are the frame numbers, say 1, 2, 3, 4, 5, 6, 7. Say 7 frame is like that. In every 6th frame, what I am saying, first bit is the frame synchronization bit. In every 6th frame, the first 7 bits are information bits. So it happens frame number 1, if frame number 1, then next it happens frame number 7, 13 and 19. So in every 6th frame, the first 7 bits are the information bits and the last bit, that is the LSB part, is the signaling bit. But in all other frame, that is all frames except 1, 7, 13, 19, all the bits are the information bit. So in that way, that is called bit slot sharing. We can use only a single channel for both carrying, that is the information bits and signaling bits carry a single channel. That is called signaling, or it is called channel associated signaling. Okay. So this is all about PCM. Application of PCM, multiplexing using PCM delta modulation and adaptive delta modulation. So in the next class, we start from the baseband receiver or data transmission technique. Okay, thank you. Now I am ending my session. Thank you so much.